Now I want to talk about the magnitude of the cross product. So this says let u and v be vectors and let theta be the angle between them. Then the magnitude of the cross product equals the magnitude of u times the magnitude of v sine of theta. Now there's a nice proof in the book on this, so I'm not going to go through this. It's just a bunch of algebra and moving things around. What I want to talk about is one of the meanings that we can get from this magnitude of the cross product. We can actually say that it's the area of the parallelogram that's generated by these two vectors. So here's the idea of what we're saying here. It says if we locate vectors u and v such that they form adjacent sides of a parallelogram, then the area of the parallelogram is given by the magnitude of the cross product. So now I'm just going to draw a quick diagram to kind of illustrate this. So here are the two vectors u and v I drew here. Now again, I just want to create a parallelogram for this. So we kind of did this early on when we were adding vectors. So I'm just going to put those in. So here's our parallelogram. So now what we're going to do is just try to drop a line down here. Not try to do, it's actually what we're going to do. So I'm just going to kind of drop a line down. I'm going to drop a line down in such a way that it creates a right triangle. Now you'll see why I'm doing this in a minute. This might not be apparent to you right now. But if we're going to find the area of this parallelogram, the formula is A equals base times height. Because essentially what we do is we would cut this off here and then move it over here, and it would actually make it a rectangle. And that's what we'd look at there. So that's the idea here. So I need to find that height. I'm going to call it a height. And this is our base here. So we have our base already. That's just the magnitude of u. Okay, but we need to find this height. So what I'm going to do here is I'm going to think of this angle theta here. And I know the opposite side is what I want to find, and then I also know the hypotenuse. So what I'm going to do is I'm just going to use those ideas. So what uses the opposite and the hypotenuse? It would be the sine of theta. So the sine of theta actually equals the opposite, which is h, over v. Now it's the length of v that's going to give us, not the actual vector v. So we have to put magnitude of v. Okay, so then if I wanted to find h, then h would equal the magnitude of v times the sine of theta. So that's what that opposite side would be of that theta there. So now we have all that we need for our formula. So the formula, the base again, it's not the vector u, but it's actually its length. So it would be the magnitude of u. And the height here, which we calculated already, is going to be v here, magnitude of that, sine of theta. Now, if I look back at my definition, not really a definition, but my result from the magnitude of the cross product, if you notice, magnitude of u times magnitude of v equals sine of theta is actually equal to the magnitude of the cross product. So I can say to find that area, it's simply u cross v and magnitude. So that's kind of a nice result of that. Now, we can go back to our previous example that I had in the previous video. And I will, because I want you to kind of see that. I actually want you to see that. So this was the problem. Now again, I can take these two vectors and say, hey, let me find the cross product of those. And we did. And it was 0, 0, negative 22. And if I wanted to find the parallelogram of that, I have the drawing here below, which is kind of nice. So I could finish that off. It would be, I think I went too far. Yeah, because that would look a little shorter, and it would do this. So that would be that parallelogram. And again, that tells me then if I just took the magnitude of this cross product, or if I knew the length of it, then that would be equal to this area of that parallelogram, which would be the magnitude of 0, 0, negative 22. And if you guys remember the magnitude is the square root of each of those components squared. So really, I would have just negative 22 squared, which would be a positive 22 squared, which actually, equals 22. And we already knew this magnitude was 22, but sometimes to kind of see it using what we're used to doing here, sometimes makes it a little nicer. So if I had to come up with a parallelogram, the area of the parallelogram for those two vectors, the parallelogram that it actually creates using those two vectors, then I would get 22 units squared. So that's what it would be. So that's one nice result that we get from the magnitude of the cross product. Simply that it equals the area of a parallelogram that those two vectors produce. And what's nice about that is we use this idea later on when we talk about surface area of three-dimensional surfaces. So it's very nice how that comes into play for us later.